So let's look at some examples of how you can put this parent function into use. So if I look at f of x equals the quantity x minus 2 squared, what is the parent and describe the transformation? Well, this gives it away, so this is the quadratic parent, the f of x equals x squared. So that's easy enough. So describe the transformation. So if I think of that expanded form and I look at this, I can clearly see the only thing I have going on right there is an H movement, which is a right or left movement. I don't have an A, I don't have a K, so I'm moving right or left. And when I go to my notes say x minus h, says I went right h units, and so this is 2 units right. So if I were thinking about what the graph would look like, here's my parent. I'm going to take this vertex and I'm going to go 1, 2, and I'm going to draw the exact same graph, 2 units. It's not going to be any bigger or smaller, it's just going to be shifted right. The next one, f of x is equal to the square root plus 3. This is your defining feature. This is the square root function, where we have f of x is equal to the square root of x. Again, describing the transformation, remember what we have, and when I think about how does this one line up, the only thing that's going on is back there, and that means I have gone up 3 units. So if I were thinking about what a sketch, here's my parent. If I take this point and I go 1, 2, 3 up, and basically every point thereafter is 3 up, my transformation graph would look like that. Now, f of x is equal to 6 times the absolute value of x. Here's your defining feature. This is the absolute value. Parent. Describing the transformation, if we think about what our rule looks like, the only thing going on there is 6, so A is 6. So it's still opening up, but it's 6 times faster growth. It's going to be that much steeper. So if I think about graphing my parent, and the absolute value graph is very easy to graph. Again, that very defined V. And when I go to graph, if I put 0 in, I'm still getting 0 out. But if I put 1 in, 6 times the absolute value of 1 is 6. If I put minus 1 in, 6 times the absolute value of minus 1 is 6. 2, I have 6 times 2, which is 12. If I put minus 2 in, I end up with 12 out. And so you can see 0, 0 at 1, 1, 2, 3, 4, 5, 6. And at 2, I'm at 7, 8, 9, 10, 11, 12. You can see how much quicker that graph begins to grow, which is what that A value does to our graph. My fourth example is x cubed plus 8. Here's my defining feature, and so this is a cubic, where I have f of x is equal to x cubed. Describe the transformation. Think about your notes. A of x minus h cubed plus k. How does this match? This is going up 8 units. So the other nice thing that you can do is you can graph a parent and the transformation kind of side by side to see the changes. So if I have 0, 0, if I put 1 in, I get 1, minus 1, I get minus 1, 2 and 8, minus 2, minus 8, my key numbers. So that graph 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And you see that key swoop. But when I go over to my transformation, when I put 0 in, I get 0 plus 8, I get 8. When I put 1 in, I get 1 plus 8, which is 9. Minus 1 plus 8 is 7. When I put 2 in, I get 8 plus 8, which is 16. Minus 2 is minus 8 plus 8, which is 0. So you can see some pretty key changes. At 0, I'm now at 8. At 1, I'm at 9. At minus 1, I'm at 7. At 2, I'm off the charts. And at negative 2, I'm at 0. And so we begin to see that swoop take place, but all of my points are up 8 units. So go ahead and try some sample problems and then tune in for the last 2 examples.